So my name is Subramanian. I'm a research scientist at Carnegie Mellon University. As Rebecca and Jonathan said, we were funded by EDF to do two projects, measuring methane emissions from the two components of the natural gas infrastructure, transmission, storage, and gathering and processing facilities. My collaborators here were from Colorado State, Dan Zimmerly, Anthony Marchese, and various graduate students and technicians, and Scott Herndon and Rob Rochelli from Aerodyne Research, and Austin Mitchell was a postdoc with us who led the gathering paper. Alan Robinson was a PI from Carnegie Mellon, and so let's see. He was my PhD advisor 10 years ago, and now he's my boss. But moving on, the funding for the study was shared between Environmental Defense Fund and industry partners. So we had Kinder Morgan, NiSource, TransCanada, Dominion, Williams, and Enable, who provided facilities, access to facilities where we could go in. So this is an example of our measurement. One of the two measurement techniques that we used in the transmission and storage facility. Do we have a pointer? Or no? Do you have a pointer? No. Oh, sorry. Oops. Okay. So if you can see the marker here, so that's our mobile lab, where we have our instruments that measure methane, ethane, tracers, nitrous oxide, and acetylene at 1 hertz or faster. And so we are here on this facility where oops, let's see. Oh yeah. So we drive around the facility, look for major sources of leaks. The nice thing about having site access is that you can determine where you want to place your tracers. And the whole idea is that you're trying to measure methane downwind of the facility. Basically, your ratio of your tracer to your methane would be will allow you to determine the facility emission rate of methane. Anyways, before I move forward, I just wanted to say something. I should have probably retooled this presentation a bit, but talking in terms of safety and pipeline safety, and a lot of this presentation is about methane emissions from all of these facilities, gathering facilities, that's gathering compressor stations, processing plants. A lot of it we'll talk about the transmission and storage compressor stations. And so methane, obviously it's a leak hazard when it's venting inside your home, it's a safety hazard, but we are approaching this from the climate perspective in terms of methane being a very potent greenhouse gas. Over a 20-year time frame, 1 kg of methane is the equivalent of 86 kilograms of carbon dioxide. And so the concern is that if you're replacing coal power plants with natural gas, you are reducing the amount of CO2 nominally being emitted by half, because of the lower carbon density of natural gas, but potentially leakage of methane can actually make the problem worse in terms of greenhouse gas emissions. And so the idea is to quantify the methane leaks from these facilities. The second thing I wanted to make, and this I'm not going to talk about in this presentation, we are also looking, after the EDF studies ended, we were actually funded by NOAA and the Department of Energy, NATL, to look at emissions of methane and VOCs from the different basins, the Marcellus Shale, Colorado, Utah, other places. And VOCs obviously are a big health concern and a lot of these gathering facilities and compressor stations, while they are not in your city, where there's a large urban population density, in a lot of rural areas, a lot of gathering facilities, well pads, and compressor stations are near houses, near rural areas where it's less densely populated, but still people live there, and people live downwind of these facilities. And some of these facilities do emit methane as well as various volatile organic compounds, especially if there is wet gas. And so you have a lot of VOCs, and so there is a concern that you have benzene or toluene or other VOCs that are potentially health hazards. So I'm not going to talk a whole lot about that. Actually, I'm not going to talk about that at all in this one, because this is focused on the methane studies that we were funded by EDF. But hopefully, some of those results will be coming out in the next year or so. So this is basically the broad layout of the US natural gas infrastructure. You have the well site over here, and then from there, that's the exploration and production, and then you have midstream gathering and processing, where the gas is essentially collected from all the well pads, brought to a central processing facility, and converted into what is called pipeline quality natural gas, where you basically take out ethane and higher hydrocarbons from the gas and convert it into some sort of quality of natural gas that is demanded by the consumer, in which case it would be a natural gas company, distribution company down the line. And then, let's see if I can actually move this thing. And then from the processing plant, it's transmitted up through a series of pipelines. For instance, typically gas was extracted in Louisiana and Texas and piped all the way to New York and Pennsylvania. And it should be sent through big pipelines, and you would have a compressor station about every 100 miles to increase the pressure of the gas, which comes in at, say, 800 to 1,000 psi, and pump further up at 100 psi to push it for 100 miles down the line again. So that is the transmission and storage network. And the transmission, that is a transmission. And storage, you're talking about, because production of natural gas happens year-round, but consumption is very seasonal. And so you end up, amazingly enough, dumping it back in the ground and in a storage facility. And so you'd have depleted oil and gas reservoirs, for instance, that receive the gas, store it till demand goes up. Then the distribution company says in the winter, we need more gas. You pump it back out and distribute it in the distribution system. So the first part of this talk will just focus on the leaks of methane from the transmission sector, transmission storage sector. And so that is essentially about 300,000 miles of pipelines, about 2,000 compressor stations. Older facilities are often run using reciprocating compressors and that are powered by reciprocating engines. The newer, larger units are often centrifugal compressors run by gas turbines. And that's a map of the pipelines, interstate pipelines running all over the country. And so what we did for the study was basically make two types of measurements, what I call top-down and bottom-up measurements at 45 compressor stations that were, we had access from 6 partner companies. We went for 11 weeks all around the country. And one was direct on-site, which I'll talk about in a minute, and tracer flux. You saw the mobile labs picture earlier on. Half the facilities were operating. That meant at least one compressor was running, and it was either pumping natural gas through or it was injecting it into the ground, and the other half were on standby. And so bottom-up is basically the direct on-site measurement of methane emissions. This is typical. This is what the EPA recommends as part of its greenhouse gas reporting program. And that has been in place for the last 3 years, where certain companies have to report their emissions of methane, CO2, nitrous oxide, if their total annual emissions exceed 25,000 metric tons of CO2. And a lot of that is really determined by operation hours. So the more you operate, the more fuel you burn, more CO2 you emit, you cross the threshold, you report your emissions. So that is not a great model for how much methane is leaking from the facility, especially if the facility is on standby most of the time and there is a leak somewhere in the facility. But that is what is part of the EPA protocol. And the way they do it is they have a contractor or a company survey team go out to a facility, look for leakers, measure some leakers with some measurement techniques. For instance, you have a leak detection with FLIR thermal imaging. So you look for leaks, and you saw one of the pictures that Jonathan showed with the IR camera. So it's a handheld camera that we can go and look for leaks. Then if you see a leak, depending on the type of emission that is there, you either measure it, if it's less than 10 SCFM, you measure it with a high flow. Otherwise, you have turbine meters or bags. And of course, there are some concerns with some of these measurement devices. There's accuracy. The acoustic devices, also called a VPAC, has been anecdotally called a random number generator. There are some concerns over the high flow technique, for instance. And again, depending on the leak has to be detected by the FLIR camera. So if the wind is in the wrong direction, you might not even detect a leak, even if there is a leak. Some of these leaks happen at open-ended lines, or for instance, which are tall stacks, and so it might not be safely accessible, so you might not be able to measure it either. And so in our study, obviously we are extremely concerned about safety, so we didn't actually make people go and take these measurements in an unsafe manner. If there was a man lift or some other way of safely accessing the leak, they went and measured it. If not, they did not. But the idea is this is basically what the EPA greenhouse gas protocol requires, but our protocol is much more comprehensive in that you need to do a Flux survey of the entire site. Whatever leaks you find, you measure it, other than exhaust emissions, whereas the EPA often uses emission factors. And now the tracer flux, there's a top-down, as I call it, downwind dual tracer flux. So this is a typical facility, for instance, a bunch of storage tanks, a couple of exhaust burner units. And so you put your nitrous oxide tracer on one end, your acetylene tracer on the other side, and essentially they are bracketing any methane emissions from the facility in the middle. And the idea is that if you have your tracer truck driving downwind, and if it's sufficiently downwind, then all the three gases mix, and it forms a nice Gaussian plume, and that tells you that the emissions on site are proportional to the concentrations measured downwind. And we have two tracers, acetylene and nitrous oxide, which essentially act as an internal standard. So if you know that your tracers are bracketing your facility and they are well mixed, then any methane that's emitted between the two tracers should also be well mixed with those tracers. And so and you know what is the quantity of nitrous oxide or acetylene that you're releasing on site. So to determine how much methane is being emitted from that site, it's basically the ratio of your concentration of the plume concentration of your methane to your nitrous oxide downwind of that facility. So this is a lot of the data that we collected at about 40 sites where we had comparable tracer flux and on-site measurements. And it has a lot of, the green bars are venting emissions from reciprocating compressors. The yellow bars are exhaust emissions from operating compressors that we estimated using AP42 estimates, AP42 emission factors. The EPA does not use AP42, it uses something else. And where is my marker? Essentially, you'll see that the reciprocating engines that actually are running produce a lot of exhaust emissions of methane, of unburnt methane, because they're all running on natural gas. You basically are pumping natural gas through, you tap some of it off, and fuel your engines. And oftentimes with two-cycle engines, for instance, you don't burn a lot of some of the methane is emitted unburnt, whereas turbines are much more efficient, and so you don't see a whole lot of exhaust emissions of methane from turbines. And so we have two techniques, like I said. One is the downwind tracer flux, which measures the facility-wide emissions of methane. And the other is the on-site technique, which is basically you're measuring every possible leak you can find, fugitive emissions, and then you put an estimate for any exhaust emissions of methane. And the y-axis is the tracer flux facility level estimate of methane emissions from the facility. The x-axis is the individual measurements all summed up. And for the most part, about 38 out of the 40 facilities, they agree within measurement uncertainty of our techniques within plus or minus 30%. Let's see. But if you actually open up the full scale, you find there are a couple of facilities on the y-axis that are way higher than the on-site estimate, and those are our super-emitters, that sites are emitting more than 300 SCFM of methane. That's what Jonathan showed with that hockey graph. Right. And so a little bit about what is reported to the EPA. Like I said, this is the greenhouse gas reporting program. Companies have to report their emissions once a year, analyzed emissions. So we took our on-site measurements and said, okay, how much of these emissions would be reported to the EPA following the greenhouse gas reporting protocol rules? And so the difference is the SOE is our steady comprehensive estimate, and the GHGRP is what would be reported based on those measurements, and anything above 0 would not be reported to the EPA. And you can see that there are a lot of emissions that would not be reported to the EPA, either because, for instance, the red bar is reciprocating compressor venting. So if your reciprocating compressor is on standby pressurized, it's not pushing gas through, but it's waiting for gas to come in, for instance, and often happens, then it does leak. The rod packing vents do leak, but that is not required to be reported to the EPA. There are a lot of open-ended lines, for instance, where there are large emissions, but the EPA just says there is a open-ended line emission factor that you can use, and so you might actually miss large sources of emissions from that. And I'm sure anyone familiar with how laws are made in DC would know this is what happens. But anyways, the idea is that it's not comprehensive, and we find that emission factors are not correct. The second one, as you noticed, as I said earlier, your engine exhaust emissions of methane, we use AP42-based emission factors. The EPA uses a single emission factor, whether it's a reciprocating engine or whether it is a turbine. And the emission factors that are reported under subpart C are really more reflective of turbine emissions. And so a lot of these emissions that from reciprocating compressor engines would not be reported to the EPA, and that's a big source of differences between what are the emissions from a facility versus what is reported to the EPA. So the fat tail, as Jonathan said, the super-emitters skew the emissions distributions. And this is seen whether it is the red bar that is reportable under the GHGRP, the blue line, which is basically our on-site measurements, or the black line, which is our tracer flux measurement, which includes the two super-emitters. And about 50% of your emissions come from about 10% of the facilities in the case of the transmission and storage compressor stations in our study. And so a little bit about gathering and processing, and that is the midstream sector. And I had probably 3 slides that I'm going to talk about really quickly. And so you have your gathering facility where you have all your well pads. From there, you have gathering pipelines that are, and with gathering compressor stations that pump gas to a processing plant. Gathering pipelines were not measured in this study, but as Jonathan says, there is a big concern over that that needs to be looked into. But we basically went to about 140 facilities overall. That's a good selection of facilities of the partner inventory of 750 facilities and all across the country. And so these are the emission rates. The blue bars are the emissions in kilogram per hour, and the orange circles are basically the normalized emissions to methane throughput. The gathering facility, what is the methane that's being pushed through? Because we were working with a partner, we knew what the throughput was, so we could normalize the methane emissions to the throughput. And so you will see the median loss rate is 0.42%, or about 56 kilogram per hour per facility, 0.08%, much smaller for the processing plants at the other end, and 170 kilogram per hour per facility. About 25 facilities had methane loss rate over 1%. And you could argue what is a high emitter, but if your processing plant or gathering facility is losing 1% of your natural gas, that's probably not a good thing. And about 25 such facilities, in particular, there is one that is a 9% emitter. And there is, let's see if I can quickly play this picture here, this video, if this plays. Okay, so we basically went to this facility, which was this 9% emitter, as we later found out. That is compressor and dehydrator on site. It had got 3 reciprocating engines. And you basically, once you look at it with the FLIR camera and the infrared, you see a lot of emissions. And this is the on-site operator still trying to figure out how to work the FLIR camera, but at least you can see the images. And you see it's starting to vent significantly. And once we notice that, talking about, and this is obviously, these are, this could be a safety hazard, right? This is potentially could be flammability or other issues. And so the on-site observer went and talked to the, went and talked to the facility operator and told them, look, we have this FLIR camera, and they knew we were there, obviously, and we are observing this huge leak. And so they said, oh, I know what it must be. It must be a stuck dump valve. And over half an hour, they fixed it. So this is obviously, these are problems that are fixable. the issue is that a lot of gathering facilities, they are unmanned. A lot of compressor stations are also unmanned, but and processing plants in particular, they have to report to the EPA under subpart KKK, just an unfortunate acronym. But but that's why they have a lot of people on site at processing plants, which are large, well maintained, and somebody is there all the time. So they look for leaks and they maintain it well. And so when we went to processing plants, we didn't find a whole lot of leakage. But gathering facilities could be are a much bigger source of leaks than processing plants often, compared to the size, throughput that they actually process. And they are often unattended. And if nobody is there to see these leaks, nobody has a FLIR camera, for instance, there is no Google car driving around, and especially this is all over the country in places where a Google car may not be there, then you end up having these unattended leaks, which could be safety hazards. Anyway, so we use that data to actually put up a national inventory for the two sectors. I'm going to skip that. Basically, so tracer flux, we need to make the greenhouse gas reporting program more comprehensive. We need to ensure all major emission sources and sectors are included. For instance, a lot of the gathering facilities are not currently included in the EPA's greenhouse gas inventory. I think if that's Anthony Marchese who can speak better to that, but a lot of the and that was the graph that that Jonathan showed at the end. But a lot of the gathering facilities and methane emissions are not included in the EPA's greenhouse gas inventory. So we need to make the reporting program as well as the inventory more comprehensive. We need to quantify super-emitters. So this is basically the problem where you have you can think of it as just the 80-20 rule. 20% of it events cause 80% of the problems. So in this case, it's 10% of the sites that contribute 50% of the methane emissions for transmission and storage. Gathering facilities, 30% of the sites provide 80% of the gathering emissions. And so if you can identify these sites, then you can actually reduce their emissions significantly. And that's good for the climate, and that's probably good for people living near these facilities as well. Thank you. Thank you for your attention.